EMF and terminal voltage. To measure the voltage being dropped across a circuit element, you need to connect a voltmeter. The voltmeter must be connected in parallel to the circuit element you want to measure. It will measure the difference in voltage between 2 points, A and B. The voltmeter, represented by a V with a circle around it, is connected in parallel to the light bulb. The voltmeter will measure the amount of voltage dropped across the light bulb. This voltmeter, connected in series, will not measure the voltage being dropped across the light bulb. Branches in circuits that are in parallel have the same voltage drops. Voltmeters have very high resistance, so very little current passes through them. The current going this way is approximately 0, while basically all of the current leaving the battery is going to go through the light bulb. This means that the voltmeter has very little effect on the circuit. Although there are separate items to measure current and voltage, ammeters and voltmeters, there are devices that can measure both. These devices are called multimeters. They have different modes that can measure current, voltage, and also resistance. So far in this unit, we have treated batteries as ideal, which has meant that they've not had any internal resistance. In reality, batteries do not supply exactly the amount of voltage difference as advertised. This is because real batteries have internal resistance. Let's zoom in on non-ideal batteries and solve problems that involve internal resistance. A non-ideal battery is a source of voltage and resistance. The internal resistance is modeled with a virtual internal resistor, r. The voltage provided by the battery is known as the electromotive force. Electromotive force is not a force at all. By definition, electromotive force, written as EMF or epsilon, is a difference in electric potential that gives rise to an electric current. EMF is the voltage you measure when no resistance is connected to the circuit. EMF is the advertised voltage of a battery. A 9-volt battery has an EMF of 9 volts. Here, this person is measuring EMF because they're connecting their voltmeter directly to 2 sides of a battery. So there's no real circuit, there's no external resistance. We're just measuring the advertised voltage of the battery. On the other hand, terminal voltage, V sub T, is the actual voltage measured across the battery when current is flowing. If there's no circuit attached, no current flows, and the voltmeter measurement will equal the EMF of the battery, as shown here. If, however, a circuit is attached to the battery and current starts flowing, the internal resistance of the battery will result in a small voltage drop, and a smaller terminal voltage will be available to the circuit. Here's our equation. The terminal voltage will be the EMF, or the advertised voltage, minus the voltage lost to the little internal resistor. And here in Ohm's law, we see that voltage equals IR. Once again, here's our equation for terminal voltage. This equation is not on the AP equation sheet. Terminal voltage is at a maximum when there's no current flowing, and it would therefore just be equal to epsilon, the EMF. When solving for equivalent resistance in a circuit, the internal resistance of the battery is considered a resistor in series. So the resistance of the entire circuit will be all of the external resistors plus the internal resistance of that internal resistor. So we're going to solve problems by treating little r here as just another resistor. So see how we have our battery over here now, and we have this other little resistor right here. This equation is not on the AP Physics 2 equation sheet. If asked to solve for terminal voltage, just take the advertised voltage and subtract the voltage dropped across little r. Use Ohm's law to calculate the lost voltage. If you're given the internal resistance of a battery, just treat it like another resistor that has been added in series. A battery with an EMF of 12 volts and an internal resistance of 0.5 ohms is connected in series to a 15 ohm resistor. What is the current in the circuit? Alright, so first we're going to solve for the equivalent resistance of the entire circuit. This circuit has two resistors, the internal resistor and this external resistor. They're in series with one another, so we're just going to add them together, and we get an equivalent resistance of 15.5 ohms. Then we will use Ohm's law. When using Ohm's law, make sure to plug in the EMF of the battery and then the equivalent resistance of the entire circuit. That will give you the current leaving the battery, 0.77 amps. A battery with an EMF of 12 volts and an internal resistance of 0.5 ohms is connected in series to a 15 ohm resistor. What is the terminal voltage of the battery? In the previous problem, we found the current in the circuit to be 0.77 amps. So now to find terminal voltage, we can use our terminal voltage equation. Essentially, we're just taking the advertised value of the battery and subtracting the voltage drop of the internal resistor. The voltage drop there would be equal to IR, that's Ohm's law. So the current going through the circuit was 0.77 amps. The internal resistor is 0.5 amps. So we subtract the voltage drop of the internal resistor and get 11.6 volts. Another way to solve this problem is by using the fact that we already found the current in the circuit. So therefore, we can now ignore the internal resistance of the battery and treat the circuit as if it looked like this, right? We pretend this is just a battery with no resistance, where the actual voltage is the terminal voltage. And now there's just one resistor in the circuit. So we can use Ohm's law. The current is 0.77 amps, which we already found. The external resistor is 15, and we get 11.6 volts. The terminal voltage is the voltage that is being provided by the battery after the internal resistance of the battery is considered.